Hello, my name is Sangwon Jeong, and I will be giving a presentation on a work called Concept Lens, visually analyzing the consistency of semantic manipulation in GANs. Generative models have become very potent in recent years, and they are showing even more potential in our everyday lives in the areas of content creation and content editing. Although some of the generated contents may seem flawless, they are not without problem. Let's take the following example. A user have generated an image of a person but wanted to give this person a white hair. The goal is achieved, but it seems like his age is also changing with. Now let's look at the second example. Here, the exact same steps in the latent space does not manipulate the same semantics on these two images. The two exemplifies entanglement of semantics and local behavior of the latent space inside a generator. To use generative models to their full potential, we need a visualization to study such manipulations and their properties. Therefore, in this work, our goal and contribution is to present a visualization design that permits navigating the various types of semantics that can be manipulated in generative models. Second, we introduce a bi-hierarchy visual encoding to help users relate latent space codes with concepts. Lastly, we show how our design, termed Concept Lens, allows users to discover concepts that offer consistent semantic manipulations, as well as diagnose concept discovery methods and their potential trade-offs. A semantic manipulation portrayed in the previous slides is what fuels content creation and editing. These manipulations can be found in various ways: supervised, unsupervised, or even text guidance. To understand semantic manipulation, we need to first know what a latent space is. Here, I am portraying what a latent space looks like in an overly simplified way. Let's look at this two-dimensional plane and say that this is a very high-dimensional space. These individual points in the latent space are called latent codes. They correspond to each of these faces. Next, the line here are called directions. And what they do is that they bring about some change in the latent code. In this case, the resulting latent codes show faces where mouths are closed. Luckily, in this case, they are semantic, meaning that we can easily name those directions. The problem is that we cannot really know a priori if any of these computed directions will behave the way we expect them to behave. Therefore, we've designed a visualization that lets users interactively explore these manipulations and codes regardless of the model, domain, or the number of such manipulations. We will now explain our visualization design. Our visualization can be largely divided into three views: a code hierarchy as a vertical icicle plot on the left side, a direction hierarchy as a horizontal icicle plot at the top, and a bi-hierarchy view in the middle. A code hierarchy created using agglomerative clustering organizes a large sample of latent codes into clusters of similar ones. And a direction hierarchy, also using agglomerative clustering, organizes a large sample of directions into clusters of similar ones. Finally, bi-hierarchy shows a Cartesian product of the code hierarchy and concept hierarchy, revealing on-demand detail of all possible combinations of code direction pairs. To make data exploration easy, we encode each node's behavior using two metrics: edit magnitude and edit consistency. The edit magnitude measures the magnitude of semantic change. A small edit magnitude would indicate that the direction is not making change to the image. On the other hand, edit consistency measures how semantically similar are the changes within the node. To effectively encode these metrics, we use a bivariate color encoding scheme. Bivariate color scale is designed to emphasize each of the extremes for our two measurements of assessing individual nodes explained in the last slide. By encoding extremes as saturated colors, they are going to stand out more compared to other nodes that are desaturated. To give some example for interpretation, the top right corner corresponds to high variance and high magnitude nodes. Directions in these nodes tend to make larger semantic changes such as age or gender, but the node may include multiple of such semantic manipulations. I'm going to show some of the use cases for using visualization. First, let's look at the code hierarchy. We can clearly see that codes belonging to the clustering at the top tends to be less sensitive to all of the directions, while the bottom group would get changed a lot, but in an inconsistent way. Likewise, in the direction hierarchy, we can see leftmost group that clusters directions will induce a large and consistent change. Meanwhile, the middle group are likely directions that induce small and somewhat inconsistent change. Users can decide which nodes to explore given this global summary. Next, we can get a summary for a specific group of codes in the latent space. The highlighted code node seems to be grouping predatory wild animals, what seems to be female lions and jaguars. The selected node in the direction hierarchy are direction nodes that manifest large changes, while the left node does so less consistently compared to the right node. We can easily see that the left node includes 2 different manipulations, while the right only has 1. We presented concept lens that provide an interactive window for exploring global and local behavior in the latent space of any generative models. Our method is adequate for exploring the behavior in the latent space because we reveal a code direction joint space. Also, our method is scalable because any generative network can be studied if it has any form of manipulating its generated output. We plan to expand our work by comparing multiple concept discovery methods to show that our method is even more generalizable in the future. Thank you.